A bit more of a challenging example would be, this is another system, predator-prey models. Okay, it's an example of what's called predator-prey model, which helps explain what's called the balance of nature. For example, if there gets to be too many foxes, there won't be enough rabbits, so then the fox population will drop. When the fox population drops, then there's going to be more rabbits. Then when there's more rabbits, the fox population goes back up again. It's amazing how this is all working as well as it does together. The whole environment is one massive, massive predator-prey model. So let's assume, boy, would that be a big system if we included all possible animals. Ooh! Let's assume we're tracking two populations, predators, let's say foxes, and prey, let's say rabbits. And x of t is the number of foxes at time t, y of t is the number of rabbits at time t. With limited food, the fox population would decline according to the model. Well, this is just the usual decay, exponential decay model. And with an assumed unlimited food sources, the rabbits would grow according to the same model, only of course this is getting bigger, so it's growing with d a positive number, right? In addition to the natural decline of foxes, the fox population would grow jointly with a number of foxes. After all, it takes two foxes to make baby foxes, and rabbits present. Now, foxes will grow according to the number of rabbits present because that's a food source. So the actual model for the fox population is dx dt equals negative ax, the natural decline, plus b times the product of x and y, because it's varying jointly, right? Increasing jointly with the number of foxes and the number of rabbits. So the rabbit population, a little bit different story, but also modified by the presence of foxes. There's a decline in rabbits proportional to the number of foxes present from predation. And the number of rabbits also, it'll decline according to the number of rabbits, because if you have a large number of rabbits, there'll be a food shortage. So the model is change in rabbits with respect to time is dy, that's, more rabbits increases their size of the rabbit population, equals negative c, because we're dropping jointly with the number of rabbits and the number of foxes. So we have the following system of equations which should track both populations, and here it is. I admit I took this one and factored out the x, and I took this one and factored out the y. So there is the system of equations that would be for our predator-prey system. Granted, we're not going to solve it now, we're just going to say why these things arise in nature. We'll look at how to solve systems of differential equations, but to the best of my knowledge, that's in Unit 4 or 5. So, this model, not this model, this model is called the Lotka-Volterra predator-prey model, and we can't solve it for elementary functions x of t, y of t, but we can solve it with a table of values or something similar using numerical methods. And here's a graph of what the situation looks like. Keeping in mind this prey might be rabbits in hundreds and the predator might be foxes in foxes. Like one dot here, this is 500 foxes, but this might be 40,000 rabbits or something like that. So, but you can see what happens as the number of prey goes up, then the number of predators goes up and reaches a peak. And the problem with that peak is, well, now there's no rabbits, so therefore the fox population declines. What happens when the fox population declines? Well, then the rabbit population goes up. See, fox population declines, rabbit population goes up. So that is very typical of a predator-prey model, and the spikes, as usually noted, the prey isn't measured in the same unit, so I just already told you that. So we can see how a spike in one causes a spike in the other eventually. So it's amazing, and that is what we call the balance of nature.
Unbelievable!
It is kind of unbelievable that it works as well as it does, isn't it?